Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing on with some more examples of determining eigenvalues and eigenvectors for different matrices. This video, we're not going to introduce really any new theoretical results, not until really our next video where we'll get into section 7.2. This one is more just going to be computationally looking at some different cases of finding eigenvalues and their corresponding eigenvectors. We will see some interesting cases though, because as we discussed in the previous video, the concept of the characteristic polynomial, as we know for a matrix, is going to guarantee that we can never have more eigenvalues than the size of the matrix. But we will see some examples in this video where we will have less eigenvalues than the sort of size of the matrix or the degree of the polynomial, and talk about what can happen in those situations. We'll also see an example of what to do when we get complex eigenvalues, even though we actually have a matrix of real coefficients. So let's jump in and take a look at these computational examples. So in this first one, we've got this 3x3 matrix here, 3, 1, 1, 0, 2, negative 2, 0, 2, 2. We'd like to find the eigenvalues and their corresponding eigenvectors. So as always, start with trying to determine the eigenvalues. So we want to determine eigenvalues. So we need to take the determinant of a minus lambda I, so 3 minus lambda 1, 1, 0, 2 minus lambda negative 2, 0, 2, 2 minus lambda. So there we go, and we need to set that determinant equal to 0. This one should be pretty easy if we cofactor expand along the first column, right? We should get 3 minus lambda, and then the determinant of this minor here. So 2 minus lambda minus 2, 2 minus lambda equals 0. Then, of course, this determinant can just be done as the diagonal minus the anti-diagonal. So 3 minus lambda times parentheses 2 minus lambda times 2 minus lambda minus negative 2 times 2. And then we can go ahead and expand that out. That's 3 minus lambda. Here we get lambda squared minus 4 lambda plus 4, and then it looks like we get another plus 4 equals 0. Now notice that since there's only one product here, this 3 minus lambda is already a factor, so we already know that lambda equals 3 is a factor. We just need to figure out the sort of roots from this quadratic component right here. So we get 3 minus lambda, and then lambda squared minus 4 lambda plus 8. We can try some factorizations here. Looks like they would both have to be negative, so things like negative 1 and negative 8, or negative 2 and negative 4. Unfortunately, none of those work, so we might want to actually just go ahead and use the quadratic formula here. This guy, as we mentioned, this guy over here gives us lambda equals 3, so we know that that's one of our roots. Over here, though, we'll have to go ahead, we'll just do a different color to make it look nicer. Let's go ahead and set this guy equal to 0. We can go ahead and use quadratic formula and get that lambda should be 4 plus or minus the square root 16 minus 4ac, so that sounds like 32 over 2. And we should be able to see here that this is actually going to be our computational example of a complex eigenvalue, because this right here is going to give us a complex value. So this is going to be 4 plus or minus. This is going to be negative 16 in here. Square root of negative 16 is going to be negative 4i. Or sorry, excuse me, not 4, negative 4i, 4i divided by 2. And then we can divide that 2 in, and it looks like we get 2 plus or minus 2i. So this is, again, going to be an example where for a 3x3 matrix, we actually get 3 different eigenvalues. But in this case, 2 of them, 2 plus 2i and 2 minus 2i, are going to actually be complex. So keep in mind we have lambda equals 2 minus 2i and 2 plus 2i. So as it sort of should be unsurprising here that if you have complex eigenvalues, you're going to have them in conjugate pairs, because remember, these eigenvalues are really the roots of this characteristic polynomial. And as you guys know from your sort of study in algebra of polynomials and solving polynomials, if you have complex solutions to a real coefficient polynomial, those are going to always come in conjugate pairs. So if we get one complex eigenvalue, we're guaranteed to have its conjugate as an eigenvalue as well. We'll see that that conjugation also actually has a relationship with the eigenvectors once we get to those. So we've got 3 different eigenvalues here. We want to go ahead and find their corresponding eigenvectors. So let's go ahead and do that on sort of our next page here. All right, so let's start with the eigenvectors for lambda equals 3, our first one. So what that means is we're going to subtract 3 off the diagonal and then solve the corresponding homogeneous system of equations. So we're going to have 0, 1, 1, 0, minus 1, minus 2, and 0, 2, minus 1. And then we're going to be augmenting that with 0, 0, 0. All right, and again, that's coming from doing a minus lambda I with lambda being equal to 3. So first things we can do here is we can take R2 and replace it with R2 plus R1, and we can take R3 and replace it with R3 minus 2 rho 1. So we get 0, 1, 1, 0, and then 0, 0, minus 1, 0, and then 0, 0, and then minus 1, this looks like minus 3, 0. Okay, now we can use this guy to clear out the one below, so we can replace R3 with R3 minus 3R2, and looks like we get 0, 1, 1, 0, 0, 0, minus 1, 0, and then 0, 0, 0, 0. So we've got that there. Now we can see that, well, actually, we are going to be parameterizing our first variable here. So we're going to let x1 equal t. So then the second equation right here tells us that negative x3 is supposed to be 0. So x3 is supposed to be 0. And then the first equation tells us that x2 plus x3 is supposed to be 0. That tells us x2 plus 0 is 0, x2 is 0. So this looks a little bit weird because we're getting x3 and x2 to be 0. So does that mean that we're only getting the 0 solution, which would sort of tell us that something's screwed up? Because remember, eigenvalues are supposed to have non-zero solutions to this equation. But then do keep in mind we parameterized x1, so we actually have free choice of that. So that's where those non-zero values are coming from. So for lambda equals 3, eigenvectors have form. Every eigenvector is going to look like something like t, 0, 0. So anything in that first component and then zeros must be in the second two components there. Okay, so unsurprisingly, the real valued eigenvalue has real eigenvectors. As we will see, though, when we get to the complex eigenvalues, that means we'll have complex eigenvectors. So let's go ahead and talk about one of those. So, so for the next one here, right, we want to go ahead and take a look, right? So for the next one, I think we said, it doesn't matter which one we do, but let's go ahead and do the 2 minus 2i, that guy. So now for lambda equals 2 minus 2i, got to go ahead and subtract 2 minus 2i off the diagonal and then augment with the 0 vector. So 3 minus 2 minus 2i is going to become 1 plus 2i, and then 1, 1, and then 0, and then 2 minus 2i is just going to become 2i and negative 2, and then 0, 2, and 2i again there. So there we go, and we'll augment that with 0, 0, 0. Okay, we haven't done a lot of work, and to be honest, we won't really run into situations where we have complex valued systems like this, but we should see at least one example just in case. We will see some cases later on of complex eigenvalues. We won't do too much with complex eigenvectors, but at least got to have one example of it. So let's go ahead and see. It might be a little hard to see how we're going to use this guy to sort of remove this. So to make it easier, what I would recommend anytime you have to deal with complex coefficients like this is make sure that your lead value is real so that you can have an easier time working with it. That means we just got to multiply this guy by I in this case. So let's go ahead and do I times rho 2 just to make things a little bit easier. So we'll get 1 plus 2i, 1, 1, 0, and then we'll get 0. When we multiply that by I, we're going to get negative 2, and then negative 2i, 0, 0, 2, 2i, 0. And again, remember, that's just because we know that I squared, which is what we're going to get there, is really negative 1, so that's where we're getting that negative 2. Now we can see very easily that we can take rho 3 and replace rho 3 with rho 3 plus rho 2. And we should get 1 plus 2i, 1, 1, 0, 0, negative 2i, 0, and then 0, 0, 0, 0. So even though it looks a little bit weird with the sort of complex value there, keep in mind you can just go ahead and do this the standard way. We want to avoid parameterizing the first and the second. So we're going to go ahead and let x3 be equal to t. Then this equation here is going to tell us that negative 2x2 minus 2ix3 is supposed to be 0. So that gives us negative 2x2 minus 2it equals 0. So that gives us negative 2x2 is 2it, and that gives us that x2 is negative it here. So x2 should be negative it. All right, let's go ahead and get the first equation then. So that tells us that 1 plus 2i times x1 plus x2 plus x3 is supposed to be 0. So that gives us that 1 plus 2i x1 minus it plus t is supposed to be 0. So that gives us that 1 plus 2i x1 is supposed to be minus 1 plus I times t. And all I'm doing there is I'm bringing these guys onto the other side and then sort of thinking about that as a complex value and then that parameter. Now, it might have been a while since you guys worked with dividing by complex values. The trick to doing this, if you want to do it in sort of 2 steps, is to actually first multiply by the conjugate here to turn this into a real value and then do normal division. So we're actually just going to make a note of that. We're going to multiply both sides, multiply by 1 minus 2i. Now, 1 plus 2i times 1 minus 2i is going to give us 1 minus 4i squared, which is going to come out as 1 plus 4, which is going to be 5. So we're going to get 5x1 equals. And then when we multiply here, I guess we'll have to actually sort of FOIL that out. Looks like we're going to get like negative 1 plus 2i plus I minus 2i squared times t. That's just sort of directly foiling this with this. And then we can sort of see that that's going to be 5x1. This minus 2i squared, that's going to become positive 2. So it looks like we get 1 plus 2i. 1 plus 3i, excuse me. 1 plus 3i times t. Then, of course, just divide by 5, and we get that x1 is supposed to be 1/5 plus 3/5 I times t. So, for lambda equals 2 minus 2i, eigenvectors will have form 1/5 plus 3/5 I times t, negative it and t. So the eigenvectors here are, you can choose anything for t, but then the second component needs to be negative I times t, and then the top component needs to be 1/5 plus 3/5 I times that t value. Now, what we're going to see is we're going to go ahead and do this one more time for this example with the other eigenvalue, 2 plus 2i, which was the complex sort of conjugate of this eigenvalue. And what we're going to see, and this is a general rule which we'll state after we finish our example, is that the eigenvector will actually be the conjugate of our eigenvectors here. So the actual eigenvectors for the conjugate of the eigenvalue are the conjugate of the eigenvectors. So let's go ahead and see that. We'll get one more page here. All right, so now for lambda equals 2 plus 2i, we need to solve. Okay, so we're going to subtract 2 plus 2i from the diagonal. So it looks like we get 1 minus 2i, 1, 1. Then 0 minus 2i, negative 2, and then 0, 2, and minus 2i, and then we're going to be augmenting 0, 0, 0. So we'll do sort of the same trick. We'll hit this second row with I, so we'll do I times row 2, and 1 minus 2i, 1, 1, 0. 0, when we hit this guy with I, it's going to become positive 2, minus 2i, 0, and then 0, 2, minus 2i, 0. Now we can use this guy to clear this out. So let's replace row 3 with row 3 minus row 2. And looks like we should get 1 minus 2i, 1, 1, 0, 0, 2, minus 2i, 0, and then 0, 0, 0, and 0 there. Okay, so there we go. Now we're ready to go ahead and solve this. Again, we will avoid parameterizing the first and second variable. So we're going to have x3 equal to t. So now we can take this equation right here, and we will get that 2x2 minus 2ix3 is supposed to be equal to 0. That's 2x2 minus 2it equals 0, which is going to be 2x2 equals 2it, which means x2 is going to be it. Okay, now we can go ahead and use our first equation. So 1 minus 2ix1 plus x2 plus x3 is supposed to be 0. 1 minus 2ix1 plus it plus t is supposed to be 0. And 1 minus 2ix1 should be negative 1 minus I times t, just gathering everything on the other side. Once again, we'll go ahead and we'll multiply by the conjugate, which is 1 plus 2i. Over here, we will get 5 again. So this will give us 5x1. Then we need to multiply this out, which we can just directly sort of FOIL. So we'll get minus 1 minus 2i minus I, and then minus 2i squared times t. So then that looks like we should get 5x1. This is going to become positive 2, so we should get 1 minus 3i times t. And then divide by that 5, and we get x1 is 1/5 minus 3/5 I t. So for lambda equals 2 plus 2i, eigenvectors will have form, well, 1/5 minus 3/5 I times t, it, and t. Now, if you go back and you compare this, right, the eigenvectors here, if you look at them compared to the eigenvectors we got here, well, we had 1/5 plus 3/5 I. Here we have 1/5 minus 3/5 I, so that is the conjugate. Here we had negative it. The conjugate of that is it. And, of course, the conjugate of a real number, t, is the same as just t. So that guy doesn't change at all. So what this tells us in general is, note, in general, if lambda is a complex eigenvalue with complex eigenvector v, then the conjugate of lambda is also an eigenvalue with eigenvector, the conjugate of v. So this is true in general anytime we're working with complex eigenvalues and complex eigenvectors. So in our next video, which will be wrapping up section 7.1, we'll look at a couple cases of what happens when we don't have an equal amount of eigenvalues to the size of the matrix.